So we are going to continue. We talked about the implicit differentiation and the chain rule the other day. So there is one more section from this chapter, chapter 2. We're going to finish it so that we'll be able to give you the quiz up to the end of this chapter. If we get time, we may get a couple of, something from chapter 3 as well. But let's see, and then we can practice tomorrow. So this last concept is interesting for application problems. It's going to be called related rates problem. We will talk about the rate anytime. Let me just go to my notebook and explain it for you. It's very easy case, and we usually give you 2 questions on this quiz, one on your next test regarding this related rate problems. Okay, let me just okay, so this is going to be related rate problems that we're going to discuss today. You see, anytime we talk about the rate, you know it by now. The rate in this case in calculus means the derivative of the function, rate of change. Okay, if you're going to be in physics, that rate of change would be velocity, and we already talked about it. So the situation that we're going to have is we usually, so far, a function would be given to you. Function, it would be function f. It's a function of x. You differentiate it. Derivative would be rate of change of the function or rate of change of y respect to the x. But in everyday life, there are going to be many situations that this x and the y are going to be by itself, are going to be functions of the third variable, which is time. You see, whatever you do, unemployment rate, it depends on the time. So if you talk about the rate of your revenue, rate of your cost, all of them would depend on the variable t, or the time. That different time you're going to have different rates. So this is the concept that we're going to talk about. Let me write it down so that you can see it when I'm talking about it. At the end of the day, it is just a kind of chain rule formula that will solve the problem for us. Okay, so let me just, as I go on, give you these definitions that we have. So what is rate first? Okay, so we recall that so far this is what we mean by rate. Okay, recall that if a function is given to you, that okay, if a function, y equal to the f of x is going to be differentiable. Okay, if it's going to be differentiable, means you can find the derivative of the function. Okay, differentiable, then the derivative of the function y prime of x, okay, y prime of x equal to the f of f prime of x. Remember, this is the one we call it rate of change. So is what is the rate of, is a rate of change of the function, or the rate of change of the y, is the rate, okay, rate of change of the variable y, but with respect to that variable. So it's going to be with respect to, I'm going to use this expression quite a lot, so I'm going to abbreviate it from now on. So, or with respect to. Okay, it's going to be rate of change of the variable y respect to the variable, okay, respect to the variable x. This is what we've been doing so far. Okay, a function is given to, the derivative of the function will be rate. Okay, c of x is a cost function, so that will be rate of change of the cost of the production at x. We are going to use the so-called differential notation for this one in this section. So in this case, this notation would be useful. Y prime, okay, or in this case, dy dx. Y prime or d of dx is going to be called simply, is going to be the rate of, okay, the rate of y with respect to x. Okay, if it's going to be moving object, you know that that would be the velocity. So this is the usual practice that we did have, so far. But as we talk about it, the situation is, you see, if you have the x and the y here, it's going to be just a point. So it's going to be a point on the xy coordinates. So if you move this point at different times, you are going to be at different position. You see, if you get the xy coordinates, so you start from here, then at one more time, you make it, this is going to be your xy coordinates. So as you can see, at different time, you can be at different places. So what we are going to consider, we are going to consider the case that y is a function of x, and then is x, okay, this x and the y are going to be the function of the time, t, okay? It's like a composition of two functions, okay? So we compose it with this new function. So again, we identify that, that in particular, this is going to be, for the moving object, this is going to be velocity. Sometimes we call it rate. So let's check that one, and then we continue. So it would be interesting to remind you that in physics, the rate of change would be the velocity, okay? In particular, if y equal to the f of x is the position, okay, this is the one that we did before, and you did it on your test, is the position, is going to be position of a moving object, moving particle. If this is going to be the case, then you know that dy dx is just the velocity. Is the instantaneous or just velocity? Okay, it's going to be velocity of the object. That reminder would be useful. So the rate and the velocity would be the same. Now what we're going to do is we are going to consider the fact that at different times you're going to be at different position, okay, when you move on. So this is going to be the case then, say if the variables. Now we go to the everyday life. If the variables, they are going to tell you this fact, okay? If the variables x and y are going to be the function of time, are functions, okay, they are going to be functions of a third variable, third variable, it's going to be third variable, which is the time t. Okay, if this is going to be the case, then your x in this formula is going to be a function of t, okay? So then you are going to have, you can consider your x as a function of t is going to be x equal to the x of t, okay? And your y can be considered as a function of t, you see? So, with this idea, you can give us your position at any time. So as you can see, these functions, they are by themselves new functions, they are function of time, so they can be differentiated. If it's going to be differentiable, of course, you find the derivative with respect to the t. For example, x can be t squared minus 2t, for example. Y can be sine t, okay? So you can differentiate each one of them, but you differentiate respect to the t. So if these functions are going to be differentiable, okay, if these functions or those functions are going to be differentiable. Of course, they are going to be differentiable with respect to what? Respect to the t, remember. Differentiable with this new variable respect to the time t. Then what they're going to have? And then their derivative would be what? So you are going to have something like, you can call this one x prime, which is going to be x prime of t, derivative respect to the t. And then the next one, you can call it y prime, which is going to be y prime of the t. But if you want to write it down in rate form, differential form, this x prime is going to be dx derivative, but the rate respect to the t. Okay, it's going to be rate of x respect to the t, which is going to be x prime of t. Okay, and the other one is going to be what? Is the rate of the y respect to the t. It's like the velocity, which is equal to the y prime of t. Okay, so in this new form is going to be, so dx dt. Dx dt is the velocity of the, in the direction of the x, if you like, or is the rate, is going to be the rate of x this time with respect to time t. Okay, this is going to be the one, and okay, and that dy dt is going to be what? Is the rate of, it's going to be the rate of y with respect to time t. Okay, so far you have a kind of three types of rates. You see, originally you have a dy dx. That's the rate of the y respect to the x, ordinary derivative. But if you go inside the variable and you assume that they are a function of the time, or compare it with the time, so they can have a rate or derivative with respect to the t over here. So we have dy dx, dx dt, and the dy dt. So what we like to do is, can you connect them together? So how are we going to connect them together? You see, go back to your function. What is your function? So the function is, note that your function, remember, your function was y equal to the f of x. But now this is going to be a new one, because your x is a function of t and the y is a function of t. So if you substitute for x, you see, if you substitute for x, the result would be a function of t. So you are going to have y of t equal to the f of x of t. You see, that's going to be the relationship this time. Now we can differentiate this one. If you differentiate this form, you see y prime. This is the composition of two functions. Outside function is f, inside function is x. So if you want to differentiate it with respect to the t, you have to use the chain rule. Okay, so by chain rule, chain rule formula. So y prime of t is going to be what? Derivative of the outside, f prime of x of t, okay, times derivative of the inside, x prime of t. So it's nothing else. Even when you substituted, everything would be a function of t. But you see, look at this notation that you have. So change this notation into the rate notation that you have. So what's going to be the rate notation? Y prime is the rate of the y respect to the t. So that gives you dy dt is equal to, okay, that is going to be the case, f prime. Remember, f prime is the original function, f. So this is going to be original function, you differentiate with respect to the x. So this is going to be a rate of y respect to the x, dy dx. X prime is the rate of x respect to the t. So that gives you dx dt. It's nothing but the chain rule. You see? This equation is going to be called related rates equation, because we just relate all the possible rates. Okay, this equation is going to be called related rates equation. You see? So in all these application problems that you're going to have, you are going to have like the situation that I put over here for you. So what you are going to do is, you see, dy dx is always can be found because this is derivative of the function. But these two rates, the rate of the x respect to the t and the rate of the y respect to the t, one of these would be given to you. When you read the problem, one of them would be given. You just substitute in this one and then get your related rates. You know, you get the unknown that you are going to be interested in. And this procedure that I did, we do it for all the problems. Okay, so the situation in any case in everyday life that you're going to have, cost function, revenue function, growth functions, decay function, if you want to find the kind of the rate of the decay, okay, at different times, you have to go through this formula that you're going to get it. Again, you know, it's just chain rule type. So you have to organize your problems and then use this formula to find the unknown rates. So what I'm going to do, it depends on the future, what discipline are you going to be? If your discipline are going to be, you know, you are not, of course, because you're taking calculus 1. If you're doing a business, so you are going to have rate of the cost, rate of the revenue, and the rate of the profit. When I teach business calculus, I just focus on those examples only. But in your case, we have to give you something, you know, from, you maybe something from biology, something from physics, something from chemistry that you are going to do in future. So what we are going to do, I'm going to give you something like 4 different cases that give you the idea of how we are going to design these problems. So these 4 problems, I mean, we don't need any, any previous information, if you like, anything hard to know. So that help you to see how to design these type of problems for future, okay? And we usually give you 2 of these 4 on your next quiz and the test. So that was just the idea of the designing the model, if you like. So we're going to check it. Okay, so in practice, you should have this equation to be able to differentiate it. But anything you differentiate, you have to multiply by its rate. We talk about it. They are going to give you the hint that these functions are the functions of the time t. So one of these, dx dt or dy dt, is the one we call it the known rate. The other one is missing. The missing one, we call it the unknown rate. So you identify it, you substitute, get it. Easy problem, okay? So any question on this model? Let's give you an example to see what's going on, to get to get a better understanding. So the first example that I'm going to talk about is going to be a kind of abstract problem, because you have a collection of this in your book. So the abstract one, we do just as I did here. But then we just give you those application problems from everyday life, okay? So there are some very famous examples, you know, if you be interested in geometry, be interested in physics, okay? But the one that I'm going to pick are easy to handle. We get there, yeah. Okay, so that's the first example. This is kind of warm-up, okay? Because we don't usually give you this one on the test. But it's nice to know, to see how you have it in abstract form, how the machine is operating. Then we come back to it. So pick a couple of them in your assignment. You get quite a lot. So this is it. Example number 1. Are you ready? So they have to give you the hint that there is a third variable. So they say that suppose, okay, suppose x and y, X and Y are differentiable function. Differentiable. Okay, differentiable functions of the time t. Okay, of time t. Now you realize that this problem is related rate problems because X and the Y are the function of the derivative of t and are, okay, these are going to be one differentiable function of the time t and are related, that are related, if you like, by the following equation. Okay, by the equation, they have to give you this relationship. Following equation. Equation is simply y equal to the x cube. Okay, that's the starting point. So this is a relationship between x and the y, but we know that x and the y are, okay, are function of t. Then they ask you this, find dy dt. You see, this is the rate of the y respect to the t, or just the velocity. Then, because at what time? When do you want us to find it for you? When x is equal to 2 and dx dt is equal to 4. This problem is an abstract problem. If it's going to be an application problem, they would have units. You see, they are velocity. So they give it to units, okay, miles per hour, you know, miles, kilometers, centimeters, inches, yards, etc. Okay, so this is the problem they're going to have. We're related rate problems. So what you have to do, you have to set up this problem. You have to identify what is going to be the known rate. This is the way I do it. You know, you can summarize it on the when you do the test, but it's nice to identify this for you, even if you don't want to write it, you know, all together. But I prefer to do it in this form: solution. So we know that this is a problem of the related rate problems. So you have to check to see which rate is given to you. You see, this is the one we refer to it as a what is given rate. Given rate. You see, your variables are x and y. So the given rates are going to be either dx dt or dy dt. In this case, dx dt is given to you. So you identify this one for yourself. So the given rate is dx dt is equal to the 4. That's a given rates. Okay, so you read the problem of the first thing to identify is going to be read the given rates. Any question? When dx dt is given to you, the unknown would be the other one. Unknown rate. What is going to be the unknown rate? In this case, clear, dy dt is missing. Dy dt is missing. But when do you want that? Okay, is there any extra condition? Yes. We wanted when x is equal to 2. Because at different time, you're going to have different rates. Okay, we wanted when x is equal to 2. You see, that's going to be the given and the unknown. Any question? Next, you have to find an equation between x and the y because you want to differentiate. You have to find an equation between x and the y. This equation we refer to it as a related equation. How are we going to relate this together? Related equation. In this case, it's given. That's going to be your challenge. You have to find it yourself in the application problems. But over here, it's already given to you. So your related equation is going to be y equal to the x cube. That is the setting of this problem up. Any question? So read it carefully, identify for yourself, given rate and known rate, related equation. Now, you are going to differentiate this using the chain rule or the implicit differentiation. then substitute these numbers and you get it. That's it. So what we're going to do is we are going to differentiate. I just explain it for you, but you can do it right away. Differentiate this equation, y equal to the x cube, but remember, with respect to time t. Because we have, we can differentiate respect to the x, or we can differentiate respect to the t. So we have to use the differential form, no prime here. It would be confusing. Okay, so there you are. We differentiate, we say that for the y respect to the t, it's going to be y prime, but it's a y prime of t. So it's going to be rate of y respect to the t. You see, this is it. Or if you like, the derivative of y is 1 times the rate of the y. Is like the implicit differentiation. Okay, now the other one, derivative of x cubed, power rule, 3x squared. But times the rate of the x is like the u prime. The rate of the x is dx dt, respect to that. This is the way you write it down. Okay, I gave you the formula. You see, this is the formula that we did have, but I don't want to use it. You see, that last formula that we did. D by dx is 3x squared that you got, times dx dt. But it would be better to, anytime you differentiate the variable in this part, use the power rule times the rate. Power rules times the rate of the variable. Over here, you see, the derivative of y, if you like, is 1 if you use the power rule. That times the rate of the y, dy dt. X cubed would be 3x squared, but remember, inside the x, there is a t. It's going to be dx dt. Okay? This is the one that we find. This is related rate equation. Related rate equation. Okay? Okay, related rates equation. You connect them together. Now bring the known information and find the unknown. So what do you have? Okay, the information that we have, you see, I just remind you, you have the dx dt, which is equal to 4. And you have the x is equal, you want to find the d by dt. It's missing, but it's missing when you want to find it, we need the x. You find it at x equal to 2. Okay, substitute. So that's it. D by dt is going to be equal to 3x squared. 3 times what is x? X is 2. 3 times 2 squared. Times the dx dt. Dx dt is 4. That's it. So simplify, then you're done. 2 squared would be 4. Okay, so it's going to be 3 times 4 times 4. 4 times 4, 16, 48. There is no unit here, but in the problems, because this is the kind of velocity rate, it's 48 in this case. And that would do the final answer. Any questions? So this is the way you handle the actual problem that you're going to have. But I just didn't create the situation. So I just go with the abstract form. So there must be an equation between x and the y. There must be an equation between x and the y. And you are going to be told that there is something inside the x and the y. That's a t. So you want to find the rate of the x. Okay, so one of these rates would be given in this case, dx dt given to you. Okay, that's going to be your known rate. The unknown is d by dt. You have the x equal to 2. Your equation is y equal to the x cube. You differentiate it. Or if you don't like to write all this information, differentiate right away. When you differentiate, you must be careful. Don't use prime. You may be confused. Okay, the rate notation. So this would be derivative of it's going to be kind of y prime as we did it before, but it's going to be dy dt because we differentiate with respect to the t. Then x cubed, chain rule, power rule, it's going to be 3x squared, but kind of times of u prime that we did before. It's going to be kind of times it by x prime. but x is a function of time. So times the rate of the x, okay? Any variable, you differentiate, multiply by the rate of that variable. So that give you equation between the rates or related rates equation. Now you substitute and you get your result and then you're done. Any question? That's a warm-up, of course, okay? But you have, a list of, okay, you have a list of these type of problems in your book. So we will pick a couple of them. So get to know them. Now go to the everyday life problem, okay? We give you 3. So out of those 3, we are going to usually question you on 2, okay, on this quiz, and 1 on your next test. So let's check the first problem. The first problem is very popular. They call it the balloon problem or the sphere problem. Okay, you have a spherical balloon, okay, and then you want to blow in it, expand it as you push it, if you like, and then the balloon getting bigger and bigger. So there is going to be a relationship between the radius and the volume of the balloon that we usually you're interested in. So there are different versions of this problem, but they are all the same. So you have a couple of them in your book. So that would be our case. Easy to write, you see, the equations, everything is going to be easy. So that's why we pick this one as our first choice. So pick this on your assignment. So sphere problem, we call it, or balloon problem. Sphere problem or balloon. So what's the situation? Situation is we are going to have a spherical balloon. Okay, are you ready? So this is what we have. We have a spherical balloon. Okay, that's it. The spherical. You have a spherical balloon. Okay. A spherical balloon is expanding. You blow in, helium, etc. Expanding. Okay. So what's the situation? Given that, okay, given that the radius of the balloon is increasing, getting bigger, increasing at the rate of 2 inches, okay, 2 inches per minute. Okay, so if this given that now we want to know at what rate. So the radius getting bigger and bigger, of course the volume get bigger and bigger too. So at what rate? What's the velocity? What's the speed? What's the rate? At what rate is the volume? Okay, the volume increasing. The volume increasing when the radius, okay, that's it, when the radius is going to be 5 inches. 5 inches. That's it. That's a famous sphere problem. There are 2 possibilities for this problem. This is the first one. Okay, so let's analyze it to see what is given, what's going to be the unknown. Are you ready? So, solution. And that's it. This is going to be, a sphere, if you like, that we have. Okay, so there's going to be radius. That is going to be the radius we denoted by r. Okay, and there is going to be a volume. So what's the situation we're going to have? So we set up the problem by identifying what is given rate. Given rate. So read the problem to see what's going to be the given rate. You see, given that the rate, the radius is increasing at the rate of 2 inches per minute. So that would be the rate of the radius. You consider the radius to be r. Okay, so the rate of the radius would be dr dt. Okay, so the dRt is given to increasing at the rate of 2 inches per minute. Okay, so this is going to be equal to 2. So it's going to be 2. You have to identify the, okay, that's going to be inch per minute. So that's going to be given rate. Any question? So you read to read, they talk about the radius. Okay, the rate of the radius would be dr dt. So that's a given rate. So what's going to be the unknown, the missing? So the unknown rate. Unknown rate. What is the unknown rate? You see, this is it. At what rate is the volume? So the unknown rate is the rate of the volume. Volume would be denoted by V. Okay, so the missing part is dV dt. So that would be the rate of the, okay, the rate of the volume. But you need more information at when do you have more information? Because you are going to find it as a special time, if you like, or a special place. So you got it, you see, find at what rate is the volume increasing when the radius is 5. So you want to find this one with the additional condition that the radius r is equal to the 5 inches. Okay, so that's going to be your unknown. You have to read this one carefully. Sometimes they switch it and you have it in your book. Sometimes the rate of the volume would be given to you. They ask for the radius. Okay, so 2 possibilities. So read it carefully to see it. This one is clear. Given that the radius is increasing at the rate of 2 inches per minute, means the RDT is given to. But if this is going to be the other way around, just make sure you get it right. Okay, any question? No. You need an equation between these 2 variables that you use, V and R. You need that equation to differentiate. So that equation, remember, it's going to be related equation. Related equation. How are we going to relate this together? In this case, it's a volume. Do you remember the volume of the sphere? Anybody remember this one? V equal to, we give you this formula if it's going to be a sphere on the test. Oh, of course, you can bring the formulas, but it's one of those that you have to bring. But the volume of the sphere would be V equal to the 4/3. Okay, 4/3 of the pi r cubed. That's the equation that we expect you to know it. So there is one problem, we call it circle problem, and this is the volume problem. The circle is the one that we are going to do, I think, during the practice quiz that we do tomorrow. But in the case of the circle, you use the area of a circle because the circle is not three-dimensional and the volume doesn't make sense. So make a note for yourself that, you see, this is a note. Keep it, add it to your case. Area of a circle. You see the area of a circle. Remember, the area of a circle is pi r squared. Okay, so this is the area of a circle. That's a very popular problem. We don't usually do it as an example, but we do it in the practice test. Okay, so make a note and bring it to this next quiz is going to be your take-home quiz. But when you get to the test, make sure you have both of them available. Okay, this is the volume of the sphere. Okay, the volume of the sphere. This is the volume. Some people, they miss it. because of the formula only. That's why we let you bring the formula, the volume of a sphere. Okay, these two are going to be very popular for these type of problems. Okay, you don't need the circumference of a circle because that would be 2 pi r, and it's no good for us because we want to differentiate. If differentiate 2 pi r, that gives us 2 pi. So it's not going to be good. So make sure you remember it. The volume of the sphere, 4/3 pi r cubed. The circle, if it's going to be circle problem, they talk about the area, and your formula would be pi r squared. Okay, any question? Are you ready? So getting back, now we set up the problem. So what we do, remember, we differentiate this one. We differentiate respect to the t, means we're just using the power rule for each variable, but we multiply by the rate of the variable, u prime. So I just remind you again that I am going, you just do it right away. I am going to differentiate. Okay, that is going to be the case. I'm going to differentiate this equation, 4/3 pi r cubed, but I'm going to do it with respect to the time t. Again, you just do it right away. We accept it. You see, for the v, we usually write v prime, but it's a rate problem. You have to write it on dv dt. Because if you write v prime, this means you differentiate respect to the r, because r is the variable. But you want to differentiate respect to the t. That's why you have to write dv dt. You write v prime on the test, you won't get the full credit for it. Okay, question? This one. You differentiate using the power rule first, then multiply by the rate of the r, which is dr dt. When you want to differentiate it, 4/3 pi is a number, is a constant. So 4/3 pi stay the same. So it's equal to 4/3 pi stay the same. Now differentiate r cubed using the power rule, that give it 3r squared. But remember, u prime, you have to multiply by the rate of the r. Rate of the r, the velocity rate of the r will be dr dt. Any question? So for each variable, you are going to bring the rate of that variable. This is give you dy dt. 4/3 pi is a constant, so we just keep it 4/3 pi. Then r cubed, we differentiate the r cubed, it's going to be 3r squared, but we have to multiply by the rate of the r. Okay, so, and that's it. You simplify, of course, this would simplify. If it's going to be circle, you see, if it's going to be circle, you need the rate of the area, dA dt, and that give you 2 pi r dr dt. Okay, dAt would be 2 pi r, okay, 2 pi r, and I don't forget you, because this is going to be used in future for the circle. You see, you have to find the dA dt, and that give you 2 pi r, but multiply by dr dt. You have two problems in your assignment that you have to use this one. Okay, make a note of it, and it would be useful for future. So coming back here and continue to finish it. So simplify. So we have the dv dt. Okay, dv dt is going to be equal to the, that would be 4 pi r squared. Okay, 4 pi r squared times it by the dr dt. Okay, now bring the information and get the result. So what do you have? dv dt is missing. So that would be dv dt missing, equal to 4 pi. 4 pi is just a pi for the time being. Okay, and we accept everything in terms of pi, of course. R squared, R is 5. R is 5, so that gives you 5 squared. Times it by the rate of the R. Rate of the R, dr dt is equal to 2. So times it by 2. Make sure don't make any mistake. Okay, you do the power first, it's going to be 25. So that give you 4 pi times 25 times 2. 2 times 25 would be 50. 50 times 4 would be 200. So it's going to be 200 pi. 200 pi. So dv dt is going to be equal to, okay, is equal to the 200 pi. Be accepted. You can, if you like, you can use the 3.14 to get the result, but it's a volume. So we accept this one as a final answer. Okay, any question? But you have to give us a unit. Any suggestion? What's the unit for this one? It's a volume, but we want to know what's going to be the unit. Anybody wants to try? dv dt. You go back to see.
Inches cubed per minute.
Excellent. That's it. Yes, because the R was inch. Okay, that's it. Inches, the radius, the length, and the time is minutes. Yes, you have to give us the rate. So it's going to be inches cube. Okay, that's it. Inches cube per minute. Again, if you don't give us the units, you are not going to get the full credit because that's the kind of velocity. So we have to have it. Okay, check the distance, the length in this case is going to be in inches. Okay, inches per minute cube, inches per minute. And that give you the final answer. Okay, any question? That's the first problem, volume problem. So there are two other possibilities. You may be given a circle. If they give you the circle, they ask for the area. They cannot ask for the, okay, they cannot ask for the volume, of course. This one case. The other case is in this problem, the rate of the radius was given. Okay, the rate of the radius was given, and they ask for the rate of the volume. But the case in your book is that the rate of the volume is given. See if the dy dt is given to you. If dy dt is given to you, of course, everything would be the same, except that last part. Then you have a little bit more algebra because you have to solve for the dr dt. Okay, so be careful and pick more of them in your book when you do the assignment. Then you have it. Okay, so it's a very nice and easy problem because it's it's classic. And we cannot move around it. We cannot change it, match. But write it down nicely to show that you did understand it. That's the first one. Any question? Let's get the second one. Okay, before the break. The second one is quite interesting. Okay, second one is quite interesting, and there are two possibilities for this second one. You see this second one, the wording of the problem and the way you are going to do it is important. This problem is, we call it the ladder problem. You see, this we refer to it as a ladder. Okay, what is going to be the ladder problem? Ladder problem. I'm going to write it down, but I just give an idea. You see, the idea is you are going to get a ladder and you lean it against a wall. You see, this is going to be, suppose this is going to be a ladder. Okay, they usually give you the length of the ladder. In this problem, the length would be 13 feet. Okay, that's a ladder. You lean it against the wall. Okay, so this is going to be the wall. Okay, and this is going to be your ladder. Okay, so this is going to be the wall, and this is going to be your ladder. And this length would be it. Now the situation is going to be, you see, you can pull this ladder down, or you can push it up. If you pull it down, then the foot of the ladder will go away. If you push it up, the foot of the ladder would move towards the, towards the wall. So there is going to be a kind of rate, a speed that you may push this one up, or you may pull it down. And there is going to be speed for the foot of the ladder. What is going to be the rate at the foot of the ladder? Okay, going to the moving away or moving towards the wall. So this is going to be a situation you're going to have, and this is what we are going to call the ladder problem. This distance, we call it X, and this distance, we call it Y. Okay, so as you move the ladder, there is going to be a different, the rate that we talk about it, the rate that you push it up or you pull it away. So if you push it up or pull it down, so the rates that you are going to be just going to rate of Y, dy dt. But the rate at the bottom of the ladder, moving away or towards, that rate, of course, going to be the rate of the dx dt, okay? Because the distance here is y, so the distance over time dy dt would be the velocity, and over here dx dt. Okay, one of these will be given to you, either the rate of the y or the rate of the x, and they ask for the other. So you have to set it up carefully, especially the way you are going to pick this x and the y, and you connect it with the problem are going to be important. You know, some people, they missed it because of they don't use the proper notation and they don't identify the information correctly. Okay, otherwise it's going to be a straightforward problem. So I have to write the problem, and then we set it up, and then we're done. Okay, it's a very nice problem, very popular, because that would give us your understanding of the problem, and whatever we need are going to be contained in this problem. Okay, this is it. So you have 3 in your book of this type. Okay, a 13, let's say, fit a ladder. They always give you the length of the ladder. Is leaning against the wall. Okay, leaning against the wall, as I identify it. And the important part is this expression that will be if the top of the ladder, this time slip down, pull it down, slips down the wall. Okay, down the wall at a rate. Okay, it's going to be at the rate of 2 feet, okay, per second. What is this one? Is it dx dt or is it dy dt?
dy dt.
Excellent, dy dt, you see the top. If they say the top, they are talking about the y. If they say the foot, the bottom, that would be dx dt. Okay, so this is where these 2 problems are going to be different from each other. Okay, so be careful. Very good. So if this is going to be the case, then they ask you for the other one. How fast? Okay, how fast will this time the foot of the ladder or the bottom? The foot of the ladder. Okay, the foot of the ladder be moving away this way. Okay, moving away from the wall. Okay, that's going to be 1. But when you want it, when the top is 5 feet, so you have to give it this extra condition. At what time do you want it? When the top is 5 feet above the ground. Above, okay, the ground. This is the situation or the description of the ladder problem. Just said those cases, the bottom top, they can switch it to give you two different problems. Okay, we're going to set it up as we did for the other one. And we are going to do it for just go to read it and to see which is given to you. Okay, as we talk about it. So solution in this case, given one is given the rate, be careful. If they talk about the top is dy dt, if it's going to be bottom dx dt, the top, the rate of the top is given to you. So it's going to be dy and dt. Okay, this rate is given to you. They get 2 feet per second. But you got to be careful because you have to, this is velocity. Velocity would have the number and the direction. So when it's going down, be identified by a negative sign. It's decreasing, if you like. It's like this slope. When it's decreasing, it's going to be negative. When it's increasing, it's going to be positive. So make sure you write this one over here correctly. So this is going to be -2. -2 feet per second. Okay, any question? So it's a velocity, would have a direction, or just a slope. So since it's going down, this must be negative. The other one that's moving away, it's getting bigger. So that would be automatically positive. If you miss this negative, your final answer would be negative, which is not going to be correct. Okay, so this is one point to pay attention. So the unknown, of course, is going to be dx dt. So what's going to be the unknown? Unknown rate. And as you can see over here, you see they ask for the how fast will the foot of the ladder. When they talk about the foot, it means the x. So the dx dt is missing. So be careful, as long as, you find the first one correctly, the second one is clear, but more information, when do you want it? When do you want it? So they ask you how fast will the foot of the ladder move, moving away from the wall when the top is 5 feet above the ground. What is this 5? Is it X or is it Y?
X.
Which one?
X.
No.
Oh, just kidding. Y.
Top, yeah, Y. Okay, when the top, very good. So when Y is equal to the what? 5 feet. Just make sure you identify these numbers correctly, and you get it when you just look at it carefully. Okay, so the first one is important, d by dt. So the dx dt is missing, so you need extra condition. At what time, at what position are you going to be interested in? You are going to be interested in the position that the foot of the ladder, moving away when the top is 5 feet. Otherwise, they say the bottom. Okay, top is 5 feet. So that's it. This is the known and the unknown. Now you need a relationship. Remember, you want to differentiate. So what is a relationship between x and the y? This is going to be your given equation. Given. Okay, sorry, that's a related. Call it. Just want to use the same expressions. So it's going. What is the relationship? What is the related equation? I just repeat it. Get too used to it. Otherwise, you can do it right away. Okay, let's see. Look at this case that you have. You have a right triangle. This is x, this is y, this is 13. Do you know any relationship between these three numbers?
Pythagorean theorem.
Excellent. That's it, Pythagorean theorem. So it's going to be x squared plus y squared equal to the 13 squared, which is 169. Okay, 13 squared, which is going to be 169. Very good. You see, this equation is the one that you have to find it yourself. So in the case of the latter problem, it's going to be Pythagorean identities. Any question? So we are ready. What is going to be doing? What we are going to do, we differentiate this one. Differentiate both sides with respect to the t by applying the power rule, but multiply everything by its rate. So I just again just like to remind you, but you do it right away. Differentiate. Okay, differentiate both sides of this equation. X squared plus y squared equal to the 169. Remind yourself that this is not ordinary derivative with respect to the time t. Okay, derivative of x squared, the power rule give us 2x, but you have to multiply by the rate of the x, dx dt, because there is the time inside the x. Okay, plus power rule for y squared, that give you 2y, but you have to multiply by the rate of the y. Derivative 169 is a constant, is 0. Okay, for each case, x squared, we just use the power rule, 2x is a chain rule. Times that by or the implicit differentiation, either one is fine. So it's a kind of times that by x prime, which is the dx dt. The other one would be 2y times that by y prime, dy dt. Okay, so you have a chance, it's optional. You can divide by 2 because there is a 0 here. So this is going to be the equation that you have, x dx dt plus y dy dt equal to the 0. So this is going to be your related rate equation, just for your information. Related rates equation. Now you have to substitute the given information numbers to be able to do it. Let's see if you are ready. You see the information that we have is we have the dy and dt. So that's a dy dt. Okay, so what I have is I have the dy dt, just remind myself. It's a -2. So I need an x here. I don't have the x, but I have the y. Y is equal to the 5. Then the dx, okay, dx dt is missing. Dx dt is missing. So we are not ready yet. Okay, we have to find the x. So what we do is a mini application of a particular identity again. You should look at this one. That was 13. This is 5, and the x is missing. So apply the particular identity again here. So that gives you x squared plus 5 squared would be 25 equal to the 169. So x squared would be 169 minus 25 would be 144. Positive square root, that give you 12. Okay, that give you 12 feet. So that is x. Now we are ready. We are ready to go and substitute to get the final answer. So this is it. You substitute all the numbers that have. I want to finish it here. So this is what it's going to be the case. Okay, x is equal to 12, so that gives you 12 times that by dx dt is missing. So the dx dt is the unknown. Don't need any parentheses here. Plus y is 5 plus 5 times dy dt is a -2. -2 equal to the 0. So that's it. That gives you 12 times the dx dt minus 10 equal to the 0. You solve for dx dt. You move it to the other side. 12 dx dt equal to the 10. So dx dt is going to be equal to the 10 over 12. 10 12, which is going to be 5 6. So the final answer is going to be dx dt is going to be equal to 5, 6. You have to give us the unit. Remember the unit x distance was feet and the time was second. So that gives you the final answer. Okay, so I write it down here. The final answer dx dt is going to be equal to the 5, 6, and the unit is going to be feet per second. So if the top of the ladder dropped down at the rate of 2 feet per second, then the bottom of the ladder will move away. Okay, move away at the speed of 5/6. You can use your calculator like feet per second to get the result. Any question? So as you can see, it's a very nice problem. It's you have to pay attention, but it's a very unique problem again. But we like it again because you have to read it carefully, set up the problem using the proper notation and the known and the unknown that you have. You put them together, then you'll be able to find it for us. So this is going to be the one that we call it case 2. Any question? So I give you a break now. We are going to consider one more case. The next case in physics, most of the time in application problems, they're not much interested in the distance. They prefer angles, or there are some problems related to the angular velocity. Okay, you have this rolling lights, if you like a police car. Okay, you have the light is going to be moving around. So there is one problem related to this type of situation that we are going to use angle and we use a little bit of the trigonometric function. So we give it that one too, so that you get the idea. You have at least some ideas of what's going on with this problem for future. Okay, that's a 9/11. Okay, we get 10, 12 minutes. We come back and then we do the last problem to finish this one. Just give you introduction of the next section a little bit. Then we practice tomorrow. We are not going to lecture new things for you tomorrow. We focus on that practice quiz number 2. Okay, so I will break and come back and do the other part. See you then. Okay, we are going to continue. Any question? So, and that is the ladder problem. And as I talk about it, the other options, when they switch X and the Y, and you have it in your practice, practice quiz, we can do that one tomorrow so that you have both cases. And it's going to be given to you, so you are going to be able to do it, and pick the one from your book, which is the similar one. Now, I'm going to give you one more. This is a little bit different from the others as I talk about it. It's very popular. There are different formats of this problem. You have kind of 3 different formats in your assignment, and it's good to know. So we are going to call this one, they call it lighthouse problem, revolving light. This is going to be the idea for this example. Okay. We can call it, revolving light problems or lighthouse problem. Okay, revolving. Okay, that's it. This is going to be, yeah, something like revolving light problem. Light problem. Or a lighthouse, one of these, just when we refer to it. Now, what's going to be a situation I'm going to have? We say one situation is this, mostly they talk about it. And suppose this is going to be the shoreline. Okay, just a straight one. So that's going to be the case that we have. This is going to be shoreline. You go to the beach, that's one. And there is going to be a lighthouse or revolving light as a distance from the shore. Okay, that's going to be revolving light over here. So this is going to be revolving lights. And this distance usually would be given to you. So suppose this distance is 5 kilometers. Okay, so 5 kilometers from the shoreline, you are going to have this lighthouse. Or they say, antenna, etc. So as you move, the lights move around. Okay, there is going to be a spot lights, okay, along the shoreline. So that spotlight is going to be something like this. Okay. So you hit this point here, and as the light move, okay, this revolve or cycling, then this point going to the right or to the left. Okay. So there is going to be a speed, the rate for the revolving light. Okay, is going around the circle. So this type of a speed we refer to it as an angular velocity. Okay, angular velocity is going to be the velocity of this. The way we're going to discuss this velocity, we usually focus on this angle. Okay, this angle would be denoted by data or data. Okay, and the spotlight going to the right to the left, and we consider this distance to be equal to the x. So as the light move, revolve, or cycling around, so there's going to be a speed. That a speed would be denoted by d data over dt. We call it angular velocity. Okay, so there is going to be one that the speed of the light would be d data over dt. This is the angular velocity that we are going to have. Then the spotlight going to the right to the left. So there is going to be a rate for this rate, okay, for the x, if you like. So the other one would be dx dt. Okay, so in this type of problems, these are going to be 2 different rates that you're going to have. And for the problems, this rate would be given to you. The angular velocity would be given, and they usually ask for the rate of these spotlights going to the right to the left. Okay, and the other example in your book is there is a police car over here. Okay, and this is going to be revolving light of the police car, and you know that the spotlight is going to be here and they are looking for somebody. So they give you something similar. They give you the distance of the car to there is a warehouse and the police for looking for somebody around that warehouse. Okay. So it's going to be the same thing. So we are going to discuss this one because the setting up would depend on this angle and the situation is different from the distance that we did before. Okay. So I'm going to describe the problem. Okay. Describe the problem to see what's going on. Then we come back to it again. So what's the problem? The problem is describing the light that you have. So revolving. Okay. Revolving light. Okay, revolving like located. It's trading located 5 kilometers from from a straight shoreline. Okay, that's it. Shoreline turns. The light turns at the speed as constant at constant angular velocity. Okay, constant angular velocity or angular speed. Okay, a speed of 3. Since going around the circle, it's going to be a radian per minute in this case, a radian per minute. Okay, that's the measurements for that angular velocity that we have. Okay, so revolving light, the location is 5 kilometers from the shore and turning around at the constant angular velocity of 3 radian per minute. So this means this d data or dt is simply given to it. It's going to be equal to 3. So they ask for the rate that this light's going to the right to the left. So this is the situation with what? Okay, with what speed? What speed is the spot of the light? Is the spot, okay, spot of light. Spot of light moving along the shore. Moving, okay, moving along the shore. Of course, when the beam light, the beam or the beam light makes an angle, okay, makes an angle of 60 degrees. Of 60 degrees with the shoreline. With the shoreline. So this is going to be the question that we're going to have. You have to get this information correctly, okay, to locate it. One of the difficulty of the people or those people who do it is when they identify the 60 degrees. They made a mistake. They take 60 degrees to be there, which is not. You see, 60 degrees is when the beam makes an angle. You see, that's a beam light. So beam making an angle with the shore, this is the angle. Okay, this is 60 degrees. Just make sure you don't miss it. Okay, it's not data. That's the angle of the beam. Of course, you need the data to be able to do the job. So you know that this is the 90 degrees and this is the 60 degrees. So what is going to be data at that time? Any suggestion?
30 degrees.
That's it. Yes. Make sure you know this is going to be always the case. So that's one. Okay. Now we set up the problem. So the situation is going to be, as I talk about it, you have two rates to compare. So this the revolving like 5 kilometers we already identify. Okay, the angular velocity would be d data dt. So the solution is going to be, so our known rate, again, you can summarize this, but I just keep writing everything. Okay, the given rate is going to be the angular velocity all the time. So it's going to be d data dt. Okay, this is given to is 3. And okay, the unit is always the radian. Is a radian per minute in this case. But the top would be radian. Okay, so it's going to be given rate. Of course, the unknown is for the beam light unknown. Okay, unknown rate. So the unknown rate is dx dt. That is going to be the case all the time. But when you want it, when or where, when, you see, it's going to be when we talk about it when the angle of the beam is 60 degrees, but you change it to the data. It's going to be when the data is 30 degrees. Okay, you identify it on your graph if you like, the picture that you're going to provide. So you identify the 60 degrees here, and that's a 90 degrees, so it's going to be the leftover, it's going to be 30 degrees, okay? Now the crucial part is equation. So what we need is, what is going to be a relationship between these? What is your related equation that you are going to have? Now, you see, look at this. It's a right triangle. It's a right triangle. So what you're going to be interested in, you are going to be interested in the relationship between data and x. Since the data is angle, so you have to look for a kind of a trigonometric equation. So your options are going to be sine of the data, cosine of the data, tangent of the data, secant of the data. Okay, so just look at the information that you have. In this right triangle, you have the x, which is the opposite side. Then you have the 5, which is the adjacent sides. So which of those 4 functions is going to be useful? Tangent, sine, cosine, tangent, secant?
Tangent.
Tangent, very good, tangent. Because you know that the tangent is opposite sides over the adjacent. So we use the tangent. You cannot use the sine and the cosine because you don't have the hypotenuse, okay? So the equation is always tangent. So it's going to be the tangent of the data, which is equal to, the opposite side is x, the adjacent is 5. We cross multiply it, that gives us x equal to the 5 tangent of the data. That is the equation that you're going to use for these type of problems. That's why, you know, it make it something nice, different, and that's going to be the case with the trigonometric function. Any question? Now differentiate. Differentiate this equation as usual with respect to the t. You differentiate each variable as is, but you multiply by the rates. So I just again remind you, you just do it right away. Remind you that we are going to differentiate. Okay, differentiate this equation, x equal to the 5 tan of the data. But of course, with respect to the time t again. So this means the derivative of x is 1, but we have to write down multiply by the rate of the x prime, dx dt equal to 5 is a number, derivative of a tangent. Remember, the derivative of tan is secant squared. So it's going to be secant squared, okay, that's s. Secant squared of data, but you have to multiply by the rate of the data, which is d data dt. Okay, so this is going to be, that's your related rate equations. Okay, So that was a related equation that we did have. We differentiated. Derivative of x is 1, but multiplied by the rate of the x, dx dt, or x prime. 5 number, 5 times derivative of a tangent, secant squared. Secant square of the data, the variable is data, so you have to multiply by the rate of the data. Okay, question? So bring the information, substitute to get the result. So what do you have? This is it. So the dx dt is missing. It's going to be equal to the 5 secant square of the data. But remember, the data is 60 degrees. Secant square of 60 degrees times it by the d data dt, which is equal to 3. Okay, you have to find the secant of the 60 degrees. You know, the secant is 1 over cosine. Cosine of 60 degrees, you have your unit circle chart. You can find it right away. So I'm going to explain it here. You see
Did we
the,
use 30 instead of 60?
oh, yes, yeah. I said that you shouldn't miss it. Thank you. 30. Very good. Yes. So that's, yeah, the 30. 60 is the beam angle. You are right. Okay, so it's going to be 3 times side 15. So I write it down. 15 secant square of the 30 degrees. Very good. 30, not 60. Okay, thank you. This is it. Thanks. Now we find the secant of the 30 degrees. You see, you know that the secant is 1 over cosine. Secant of the 30 degrees is going to be 1 over cosine of the 30 degrees. And the cosine of the 30 degrees is radical 3 over 2. Okay, so that gives us, it's going to be radical 3 over 2. And use the reciprocal, that gives it 2 over radical 3. Okay, now you square it. So the secant square of the 30, you can do it here, but no, I just do it separately. So we square it, that gives a 4/3. Okay, so that would be 4/3. You bring the 4/3 here, or just do it all together. So the dx dt is going to be equal to the 15 times the secant square, which is 4 over 3. Okay, you simplify 3 and 5, 3 and 15, 5 times 4, 20. So this is going to be the speed of the beam, right? It's going to be 20. What's the unit for this one? X is the distance, and this the time. What's going to be the distance unit in this problem? Is going to be, yes, Geneva, you're right. The distance was kilometers, remember? It's 5 kilometers from the beach. Okay, that's one. The distance is kilometer and the time is minute. So it's going to be kilometers per minute. Okay, that's a speed. And this is going to be the final answer. Okay, it's a very nice problem because it's different from the other one. Setting up is nice, okay, but make sure you identify that angle correctly. Otherwise, it's a straightforward problem. And as I told you, your book, they say the police car chasing somebody around the warehouse, but it's the same thing. They give you the 3 different numbers, 3 different data, and they ask you to find it. So that's all we do with the related rates problem. That give you, sometimes I do the example for the business, but you are not measuring business. So that's why we don't usually, that's easy. The business one's very easy because, it's case with the revenue. And then they find the rate, the price, price demands equation that they have. That depends on the demands. They change the price. So it would be easy, but a nice problem. So get the one on your book close to what I did. Okay, for your assignments, and just we give you a couple of them. And in future, you have the idea, when they talk about different theorems especially in physics or in chemistry, rate of change is always available. Okay, and that's it. Any question? So we are done with this chapter Okay, chapter 2. There is usually one more application problems we do later. We don't need it. And we done with this chapter. So so we done with all the formulas. Okay, and the formulas that we need, we did it. Okay, let's just check. There is one section usually we talk about higher derivative. Just make sure that because in different edition of the book is different. So just check your book. We did implicit differentiation 2.5, and that's 2.6. No, this is what all you have in your book. Okay, so we go to give you an idea of you see what's going to be in the next chapter. Next chapter is going to be quite interesting. So you're done with all the formulas, okay? Everything we need for the derivative of the function, we got it. And you see at the beginning, we were looking for solving the problem of a tangent line. We did it. We not only solved the problem of a tangent line by finding the slope, so we changed the slope into the rate of change, and we solved the problem of the rate of change. Okay, so everything done nicely. But what are we going to do in chapter 3? In chapter 3, we are going to challenge another problem of calculus. Okay, it's more algebra, this chapter. So what's going to be the next problem? The next problem is, we call it optimization problem. Optimization problem is the situation that you're going to be given. There is a quantity that you may be interested to maximize it or minimize it. So finding the maximum and the minimum in these type of cases, we refer to it as an optimization problem. So this is all we are going to do in this chapter. So what we're going to do, we are going to consider a function, and we define what we mean by the maximum and the minimum, and we are going to find it. There are some nice theorems, some method to be able to do it. Okay, so this is going to be, I'll just give you an idea of how we do it, and then we go for it. Okay, that's 3.1. It's all algebra, nice. We get some theorems, some methods to be able to do it. So what we would like to do is going to be just give you, the title is going to be, we want to find so-called a relative, okay, relative extrema of a function. This is eventually what we're going to do. Extrema means a maximum or a minimum. You see, the way we are going to do what we are going to do in this chapter, really just give you an idea, is you see this is going to be a function, for example. If this is going to be a function, you see you have a peak point over here. So this is the one we call it the maximum of the function, maximum point. There's going to be a bottom of the function over here that we refer to as a minimum. So basically what we are going to do is we are going to find out how we're going to get this. Okay, this maximum and the minimum. It's calculus. So you have to relate every problem to what? Every problem to the tangent line problem. So what we can do, we can investigate what type of tangent line are going to have. You see? Horizontal tangent line. Remember, we discussed this one before. When a line is horizontal, the slope is 0. But this is calculus. The slope is derivative. So at this point, the derivative is 0. And at this point, the derivative is 0. But you get the maximum here and you get the minimum here. So one way to find a maximum and the minimum is to find the candidate. These are the candidate. So the candidate for the values of x, and that make, okay, the maximum, the minimum is that the f' of x would be 0. So this is one way to do it. But there is another case. Remember those functions with the sharp corner. So if you have this one, you see, look at this one. If this is going to be graph of your function, of course, this is the bottom of your function. So that's a minimum. So in this case, you see that was a maximum. That is a minimum, if you like. It's where your function will be maximum value, minimum value. But if you consider this graph, you see at this graph, at this point, you get a minimum here. But you can have a tangent line here, horizontal tangent line. Doesn't make sense, a sharp corner. But you can have a kind of vertical tangent line. Look at this one. Vertical tangent line. So in this case, you get the horizontal tangent line, you get a maximum and minimum. But there's going to be another possibility. The possibility that there is a tangent line, but tangent line is going to be vertical. If the line is vertical, what is the slope of that line? Any suggestion? If the line is vertical, what is
One.
this? What is the slope of that line? How much?
Is this slope 1?
No, why? No, the slope of a vertical line. Remember, the slope is what? Is rise, run. On this problem, you see all rise, 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 rise. There is no run. So remember that was rise over run. Run is 0. So rise over, a number divided by 0 is what? A number divided by 0, you say it's undefined. So in this case, the slope of a vertical line is going to be undefined, or does not exist. It's undefined now. The undefined would be better. Undefined is going to be better, but this is calculus. In calculus, the slope would be derivative of the function. So in this case, this means at this point, the derivative of the function does not exist. You see? So there are 2 places, but you know that at this point you get the minimum. So there are 2 places that you may get the maximum and the minimum of a function. The place that the function is nicely differentiable and you get a horizontal tangent line, and line would be horizontal if tangent line would be horizontal if the f prime is 0, and the place that you get a vertical tangent line, if you like. That vertical tangent line would happen if the derivative does not exist. So if a function is given to you and you want to find the possibilities of getting a maximum and minimum, this is your job. You have to find out the places where the derivative of the function is 0, and you have to find the places where the derivative of the function does not exist. This is your main job. So these are the candidates that we're going to introduce in this chapter, and we go for it. This is the thing that you're going to do for any problem in this course from now on, in this chapter at least. And we already practiced this. So these are the candidates, but the next question is going to be which one is the maximum, which one is the minimum. Then we need some theorems to be able to do it. So those theorems, there are some tests. We refer to them as a test, the first derivative test and the second derivative test. And then we finish this chapter. Okay, so that is a roadmap, a preview. Where can you find a maximum or a minimum value of a function? At the end of the day, there are 2 places that you can find it. You can find it when f prime is equal to 0, or you may find it when the f prime of x does not exist. Okay, so that is where we will get to this one, but it takes time. What is going to be the difficulty? The difficulty is you have to carefully define what you mean by the maximum and the minimum first. Okay, do this maximum and the minimum, and then go for the test to find it. Okay, any questions so far? So keep in mind, this is, some people think that the first one would be enough. They differentiate the function, they let it equal to 0, they look for the bank. No, you have to consider both cases. But before getting to this, you have to define what they mean by the maximum and the minimum value of a function. You see, when the domain would be given to you, find the value of the function on its domain. Then you get a bunch of numbers. The largest value is the maximum, the smallest value is the minimum. That's the maximum and the minimum value of the function. But what we are going to do, sometimes when you talk, for example, if I ask you, what is the maximum price of a house or home? Okay, so if you live in Oceanside area, for example, you may give us a number. But if you consider the maximum price in San Diego area, that would be a different number. If you consider in the California, would be different. So these are going to be called local maximum, local minimum, or relative. Relative to the place that you live. Okay, relative maximum, relative minimum. But if you consider the price of a house or home in the entire domain, our entire domain would be the United States of America. If you consider the maximum price in that entire domain of your function, if you like, that number is going to be called absolute maximum and the absolute minimum. So I'm going to define those first, because we have to have a good idea of what we are looking for first, and then we go for it, and eventually we get this done. Okay, so I try to give you just a preliminaries, just give you one question on that quiz. Then it will take us the next week to finish this chapter. Okay, so let's give you example definitions, and you let me know if you have any difficulty in these definitions, because they are going to be very important using through this chapter. Okay, so I give you the definition: relative max, relative mean. Some people they say local max, local mean, but we go for the relative. There you are. Suppose the function is given to me. You all the definitions today. Suppose you have a function f, we need the domain of the function is defined. On its domain, you have to find the domain first. Define on a domain of the function, or its domain, on the domain D, and C is a number. And C is a number in the domain. Number, okay, in D. So we have a function and we pick the C in the domain. Now, first, I'm going to define, I'm going to define the relative minimum of the function. Means the smallest value of the function, but in locally, in my area, if you like. So this is it, the first one. F of C, the value of the function we refer to is f of C is a relative minimum. Relative minimum is a relative minimum value of f, but we refer to as a relative minimum value of f if this is going to be the smallest value of the function, but in my region only. If f of C is going to be less than equal to any other value of the function, but only in my region for all x, okay, near C, in the neighborhood of the C. That's it. It's minimum. It's a minimum value of the of homes, if you like, in my area. It's a relative. It's a local. Some books they say local. Okay. So f of C is going to be relative minimum if this condition is satisfied. Also, f of C is absolute minimum, means the bottom of the function. Also, f of c is going to be an absolute minimum. And the absolute minimum, or the absolute minimum of f, if you see, when it's absolute minimum, this is the bottom of your function. So this means f of c is less than any other value of the function. It's going to be less than equal to the f of x this time for all x in the entire domain of the function. Okay, so that would be absolute minimum. Any question? So if the smallest value of the function, it's absolute minimum. There's only one value, the absolute minimum. But if it's going to be just minimum for a while, minimum in your area, then it's relative to your area. If you change it to the larger area, okay, then you get different numbers. So that's a relative min, relative max, absolute minimum. Okay, any question? If you switch this direction, that gives you a maximum. So repeat it again. We repeat it. F of c is a relative, okay, relative maximum this time. Maximum, of course, maximum value of f if the other way around is bigger than anything else. So f of c is greater than equal to the f of x, but only in your area for all x near c. So if you go to different region, you have different minimums, different maximum. Okay, so that's going to be relative maximum is bigger than anything else, but only in a small area. And then also f of c is going to be an, or it's going to be the absolute maximum value. Absolute means this is the largest possible value of the function. Okay, of f if larger than anything else. So f of c is greater than or equal to the f of x for all x in the entire domain of the function. Okay, in the entire domain of the function. That's a relative maximum, relative minimum. Sometimes when we don't know which one is it, but we know that it's going to be one of them, we use this expression. So since I do the expression from now on, so sometimes we say that f of c is going to be a relative, okay, relative extremum, this expression, if it's either the maximum or minimum, if it is, okay, if it is going to be a relative minimum or a relative maximum. So this is the expression that we use most of the time when we just, want to just to start to get these numbers. Okay, so you have to look at the value of the function. Okay, values of the function. You know that the value of the function is going on the y-axis, and value of the domain are going to be on the, okay, on the x-axis. Okay, so let's give you one example. We cannot give you algebraic example. We just use the geometry to just have a look to make sure you understand it. Then we are going to find a method to do it. Okay, so let's see how we're going to, because you have some problems on your book that they give you the graph and I want to identify it. So let's get to this first, and then eventually we are going to give you a theorem to find it. Okay, so let's have example. example, and this is going to be number one. It's a very popular case. We wanted to locate the maximum and the minimum for us. Okay, so this is it. Look at this graph. Okay, suppose this is going to be the graph. It's given to you. Okay. And this is going to be the other part. Okay, so you have a number here. Let's say this is equal to 1, if you like. And this portion is given to you, and this is also 1, -1. And over here, suppose this is something like 2. And this is going to be something like +2. Okay, and you can call it 3, doesn't matter. To have a different numbers. So this is the function, and we want to know if you get something like a maximum or the minimum for this one. First, you have to check the domain of the function. What's the domain of this function? Domain, how far my x going to the right, to the left? That is how you find the domain. Going to the right, to the left. Any suggestion? You see, you can go to the right, to the left, forever. Because this is going up, 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 and this is going down, 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 whatever. Okay, so the domain is going to be, yes, you're right. The domain is all real numbers. Okay, so the domain is going to be -infinity to +infinity. You need the domain. Okay, that's the domain. Now you look for the maximum and the minimum. You see there is a peak point here. So at this point you get a maximum because you get the maximum. But if you forget about the other part, you see that's 1. So at x equal to 2, the value of the function is 3. So this is going to be the case that you say f of 2 equal to 3. You see, this is a maximum. But the question is it a relative maximum or is it absolute maximum? Which one is it? You see, if it's going to, which one?
Relative.
It's going to be relative. Yes, it's a relative. Yes, it's a relative because you see, this is not the end of the function, if you like. So your function is going up, 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 up. So there are some other numbers. You see, if you pick these points, these numbers are above the 3. So if you forget about everything else, this is going to be a maximum. But if you bring the other part of your function, it's not the maximum because there are some numbers above it. Okay, so in this case, f of 2 equal to 3 is, okay, is going to be a relative. Is going to be a relative maximum. Relative maximum. Any question? So when we say relative maximum, we mean 3. If you say 2 and 3, 2 and 3 is a relative maximum point. Be careful when you talk about it. Most of the time when we talk about the max and the mean, we talk about the product, if you like, the result, the action, the output. So we say 3 is a relative maximum. But if they say how will the 3, we say replace the x by, oh, sorry, this must be a -2. I'm sorry, that's a -2. Okay, because it's to the other side. I made a mistake, I didn't identify. It's f of -2. Okay, so f of -2 equal to 3 is a relative maximum. Okay, maximum. You see -2 and 3, and we don't usually use, this is a relative maximum point, if you like, maximum point. we are going to be interested in this version, f of -3, -2 equal to 3. Is going to be a relative maximum. Okay, so that's going to be case one. And as you can see at this point, the horizontal, you see the graph, the tangent line is horizontal. You know that the tangent line is horizontal if the derivative is 0. So that gives you the idea that the f prime of -2 is also equal to the 0. Because at this point, the tangent line or the rate of change is going to be 0. So that will help you for future to see how you're going to find it. Okay, any question? So that's a meaning of a relative meaning. It's a relative because you have some other values for the function above it. So it's going to be similar for the 1. It's down here, so it's going to be minimum. And this is also a relative minimum. It's a relative because your function is going down. Look at this. You see you have these values as well. So there are many values below the -1. So this is it. Similarly, you claim that, okay, in this case, you have f of 1 equal to the -1. F of 1 equal to the -1, again, is a relative. Okay, it's going to be relative minimum. Relative minimum value of the function. We call it relative minimum. Okay, it's the same thing. Again, the tangent line at this point is horizontal. You see, look at this one. And f prime of 1 is going to be equal to the 0 for future. Because there are 2 places that you get it. Horizontal tangent line and the vertical one. So that's going to be the case. Any question? Is there any absolute max, absolute min for this one? Means, can you find the largest possible value of the function or the smallest value of the function? That's correct. Yes, the answer is no. No, we can't find the absolute max, absolute min. Because this function going on forever, up to the positive infinity, this goes up to the negative infinity. And you know that negative infinity and positive infinity, they are not numbers. So in this case, this is it. There is no absolute, we call extremum or extrema. So you cannot find the absolute maximum or the absolute minimum to get this true. Okay, so that is the situation we're going to have, the domain. Any question? Give another one. See when all of them are given at the same time. This and next one is very popular. You are going to do it eventually for us, yes, using the different formulas. That's number 1. Any question? Get the second part, second example. It's a very popular function. Okay, let me graph it, then you do it. We have the equation of this and we're going to do it. You graph it for us, but not now. So this is going to be the case. Okay. So this function is defined in this form. It is going to be a positive one and a negative one here. So we have this graph. Okay, this is a negative one, and this is a positive one. And this portion on the top. Okay, this is equal to 3, if you like. Equal to 3, but there is an extension of this function. So there is some values that you get a 3 here. And there is going to be some place that we get a -3 here. Okay, and your function is going to be in this form. Okay, it's a sharp corner here. Okay, so that's going to be the sharp corner, and you get this number on the top. Okay, so is that going to be the case? And I'm going to give you these numbers as, Okay, this numbers over here is something like 3.5, if you like. 3.5, or call it 7.5. Okay, so it's a -3, +3, -1, 1. You end up here with 3, if you like. Okay, that's going to be 3. And then on the top is going to be 7.5, 3.5. This is going to be the function that it is giving to us. Okay, that's a 1. So we want to find out the same thing over here. And what is the maximum, what's the minimum that we are going to have for this function. So let's start with the domain. What's the domain of this function? How far you can go to the right and to the left and be on the function. Any suggestion? You see, you can go up to the -3 here because they restrict it here. So, and you go up to the +3 here. Okay, so it's a solid point. So this means the domain of this function is closed interval of a -3 and 3. Okay, if there is no solid point here, it's just going up, 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 down, down, down. So in that case, you are going to get to the -infinity, +infinity, but you don't have anything else after 3. So the domain would be -3 and 3. Any question? Now relative max, relative min, or the maximum minimum. Any suggestion? And you know that this is going to be the origin. You see, look at this function, look at this red part. If you look at the red part, you get a maximum here. You see at 0, f of 0 is equal to 3. F of 0 equal to 3. If you forget about those blue parts, so f of 0 equal to 3 is going to be a maximum. But this is a relative maximum because you have more numbers above it. At least you have 7.5 here. Okay, so if you forget about those blue parts, in the red parts, we have f of 0 equal to 3, which is going to be a relative. Okay, f of 0 equal to 3 is what? This is going to be a relative. Okay, it's going to be a relative maximum. Maximum. And as you can see, the tangent line is going to be horizontal again. So f prime of 0 would be 0 for future in order to find it. So we let f of f prime of x equal to 0. One of the solution would be 0. Any question? So this is a relative maximum. Anything else? Any suggestion? Look at the possible values of your function to see if you can find anything else for us. So look at the values, possible values for your function. You see your graph is above the x-axis. So the function is go up, up, up only, not the down, down, down. So as you can see, the value of the function on the y-axis, the value of the y start with the 0. Start with the 0 and end up where? You see, it would end up at 7.5, 3.5. So the value of the function is going to be from 0 to the 7.5 that you get. Now, where are we going to get the value of the function to be 0? You see, at the -1 and +1, they are x-intercepts. So you note that, you see, you note that f of -1 is going to be what? F of -1 is equal to the 0. And f of 1 is also equal to the 0. Okay, so this means 0 is the bottom of your function. You see your graph starts from the x-axis and going up, up, up. So this means this 0 value is what? Is bottom of your function. So this means f of -1, which is equal to the f of 1, which is equal to the 0. So 0 is the absolute minimum, is the absolute minimum of your function, minimum. Okay, absolute minimum means the least value of the function. because your function starts from the x-axis. You see, this is the point that you have, then it's going up, up, up. So that gives absolute minimum. Any question? And as you can see, f prime of -1 and f of 1 does not exist because you have a sharp corner here. Remember the sharp corners. So it's good to make a note that f prime of -1 does not exist, and the f prime of 1 does not exist because they are a sharp corner here. You see, at sharp corner, we are going to have what? We are going to have a vertical tangent line, not horizontal. Any question? So that's absolute max, absolute mean. How about the absolute minimum? So absolute minimum of your function is 0. But what is the largest value of your function? You see largest value? Since the domain is restricted between -3 and 3, you see f of -3 would be 7/2. And f of 3 would be 7/2. So 7/2 is the maximum, absolute maximum of your function. Because your function end up with the 7/2. You see, the range of the function is between 0 and 7/2. So the 0 is the minimum, absolute minimum, and the 7/2 is absolute maximum. So it's a very nice example, and you will see it in future we do it. So the other option is going to be, you explain it, that f of -3 is equal to the f of 3, and both of them are 7/2. And 7/2 is the largest value of your function, is the absolute. Okay, it's going to be the absolute maximum. Okay, so it's going to be absolute maximum, and it's going to be absolute minimum. So this is a very nice example that you see the interval is closed. The domain is a closed interval. It's not surprising. We are going to prove it next week, that if the interval is closed, you always have one absolute minimum, one absolute maximum. And we're going to show you how we're going to find it. But for the time being, no algebra. We just give you an idea for this group. Okay, any question? So this is where we get the relative max and the absolute max, you see. If you can see on the red part, 3 is the relative maximum. But there is something above it. So that's something above it, 7/2, that give you absolute maximum. So in this case, you have the relative maximum and the absolute maximum at the at the same time to get these numbers. Okay, this is a very famous graph. It's going to be something like this is it. I think this should be something like this one. We are going to get the fifth root of, I think I don't remember, but it should be this one. And we are going to do it later on. We show you how we get these numbers, and that would be a very nice one, and we discuss it because the domain should be restricted. Okay, so that gave you introduction to what we are going to do later on. So as you can see, we find out that we get an idea that there are 2 places that we get the maximum and the minimum. So if you get a maximum and the minimum, you may have a horizontal tangent line, f prime is 0, or you may have a vertical tangent line. Next time, we are going to show that this is not surprising. It's happened all the time. The result's going to call Fermat theorem, and then we take it from there. So there is not going to be any question from this part on the quiz, because the chain rule is very important one. So we want to make sure we understand it before getting to the next chapter. So what we do tomorrow, we just go over that practice quiz. Okay, we spend time on that one to make sure you understand it. So check the practice quiz. I do the practice quiz number 2 tomorrow for you. And then as usual, I post the practice quiz on Friday, and it's going to be due by Monday. And next week, we take care of chapter 3. Chapter 3, very important chapter. And we get all the question from for your test 2, and a couple of them for the final would come from this chapter. Okay, that's it. So if you haven't done your test, today is your last chance. Make sure just do it. I've already got information that most of you did it. So I will collect your test tomorrow. So I will grade it over the weekend. So you will see the result before your next quiz. Okay, so read the practice quiz carefully and we go over it tomorrow. No new lecture will be given to you tomorrow because we want to make sure that you are ready for that. Okay, you are happy about chapter 2. That's the problem. Okay, any question?
I
That's-
actually have a question about
Yes.
the absolute maximum.
Yes.
Are we able to find the derivative of that one? Is it considered that there's a horizontal tangent line at 3, -3?
Since yeah, yes and no. You see, for the derivative of this is how we are going to to put this together. The difficulty is going to be this would happen at the end point of the interval. You see, at the -3 and 3.
Yeah.
If you want to talk about the derivative, then you have to talk about it so-called one-sided.
Gotcha. Okay.
So that's why we avoid it. And that's why
Okay, thank you.
For the next week, we are going to divide the problem in 2 parts. The parts that we're dealing with the relative and the parts that we talk about the absolute. But that's why we avoid it. Avoid the one-sided derivative we call it.
Okay, thank you.
Okay, very good. Any question? So tomorrow, practice quiz number 2. This is the way we are going to do it to make sure everybody happy about the change. Have a good one. Take care and see you tomorrow. Bye-bye.